We talked about oxidation. Oxidation was increasing oxygens. Reduction is going to be loss of oxygen or increasing hydrogen. Okay, so the oxidation makes the most sense for increasing oxygen. For reduction, increasing hydrogen. Okay, easiest references. The best place to get your hydrogen, you might think an acid. The acid only supplies H+. If we're going to start adding hydrogen to a structure, we need both H+ and H-. And H- isn't very stable. Okay? So there aren't a whole lot of places that we can find H-. So the easiest way to do this is to put that positive hydrogen and that negative hydrogen next to each other and use elemental hydrogen. Okay? Kind of like we did with elemental bromine. Okay? The problem with elemental hydrogen,
it's gas and it's really reactive.
It's actually not all that reactive. It in the gas state is kind of tricky, but it isn't that difficult. We can just bubble the gas through a reaction.
Is it because it's small? Like it says up there?
Bromine is massive. When we look at the pi bond, okay, that carbon-carbon bond, we can draw that up here real quickly. That carbon-carbon bond, bromine is big enough that it can pretty much bridge the gap and we can get that cyclo 3-membered ring. Okay? It's also electronegative enough that it can polarize and get that positive electrophilic bromine. Hydrogen can't really do any of the above. Okay? Which means while hydrogen would theoretically undergo the same type of reaction, it's too small, it's not electronegative, we don't get any of the polarization that we would need to get it to react with an alkene. So what do we have to add?
A catalyst.
A catalyst. And when we go through and look at the reagents listed, 3 of our reducing agents all supply H2, but they also supply a catalyst. Okay? The role of that catalyst is supposed to help facilitate hydrogen interacting with the alkene. Okay? How does it happen? I forget where I borrowed this picture from, but it's one of our textbooks. It's a fairly common figure. Our catalyst, our metal catalyst, is just a surface, okay, of atoms. Hydrogen will coordinate to that surface. Our alkene coordinates to that surface. Okay? Because they're now both connected to the surface, the metal facilitates the electron transfer between the alkene pi system and the sigma structure of our hydrogen. Okay? So that's all that the metal surface is really trying to do, is to facilitate that. Because all of the chemistry is happening through the metal surface, the hydrogen gets added on the same side of the pi bond. Okay? And so we get a syn addition. Okay? So a repercussion of all of these metal catalysts is syn addition, okay, with hydrogen. Okay? It doesn't even have to reference the metal catalyst. Remember, hydrogen is insanely small. If we go back to our category, our references, if we try to put hydrogen there, what is our leaving group? H-, which is so unstable that what does it do? It immediately reacts back, which also perpetuates our syn addition. So we get multiple considerations that force us in that syn type addition. We're putting the hydrogen on the same side of the pi bond. Okay? This means whatever stereochemistry, sort of stereochemistry, that we have with our pi bond, be it cis or trans, that gets perpetuated into the final alkane product. Okay? So we have to be aware of that and watch out for that. If we go through and look at the variety of catalysts, the first 2, and someone's going to need to check real quickly on Raney nickel, but I'm pretty sure Raney nickel does the same thing as platinum and palladium. It is a super active catalyzing agent. It just fully reduces. Okay? So it will reduce any pi bond. Okay? When we scale up to our polar pi bonds, we'll add some nuances behind that, but for the most part, if you see hydrogen and a metal, you're going to do a syn addition of hydrogen to whatever pi bonds are present. Okay? When we move down, we encounter Lindlar's catalyst and sodium and ammonia. Okay? So what do we notice as a potential difference for those two versus the ones above?
The metal is reacting.
Okay. If we look at the reactions up above, we're using platinum, palladium, nickel, okay, all kind of transition metals. Okay. If we look at the Lindlar's catalyst one, our first reagent, we'll call it red box versus now purple box. Okay. Do we specify a metal?
No.
No. Why do we go through and add someone's name to it?
Because it breaks the rules, or there's something special about it.
There's something special about it. Okay, Lindlar's catalyst is something different. Okay, and we'll address that difference in a second. If we look at the purple box, what's weird about the purple box? I just noticed I spelled catalyst wrong. What's weird about the purple box?
It's not a not a transition metal.
Not a transition metal. Yeah, I'll accept that. There's also something that's really, really, really different.
The hydrogen's on nitrogen.
Oh,
Where's our hydrogen?
it's an ammonia.
It's on nitrogen.
Okay. When we're talking about the additions of the first three reagents, we're adding H2, H plus, H minus. Hydrogen only shows up in one place in the ammonia. At best, what is the charge on that hydrogen? +1. Okay? Because it's connected to the more electronegative nitrogen. Okay? So that's at best. There is no negative hydrogen, and yet somehow we're still adding 2 hydrogens across a pi bond. So that one gets into all sorts of weird, crazy chemistry. Okay? We could also address the metal. It's not a transition metal. Okay? On top of which, where are we placing the metal? On top of the arrow. We do have to be very careful with using the arrow as a frame of reference. Okay? Because sometimes reagents are above the arrow. Sometimes reagents are below the arrow. Sometimes we just throw reagents wherever the hell we feel like putting them. Okay? So be a little bit careful with placement of reagents around arrows. Okay? But for a metal to be on top of the arrow, that seems kind of weird. Okay? Add to that, when you think sodium, what do you think of?
Highly reactive.
Sodium? Most people think about sodium as highly reactive.
Sodium metal. That's solid.
Spectator ion, that's what we're getting to. Sodium, when we think about sodium, is a spectator ion. It doesn't react. Sodium ion absolutely is a spectator ion. Are we looking at sodium ion?
No.
No. That's why that solid is typically written there, is to really draw attention to the phase. This isn't sodium ion, this is sodium metal. Sodium ion, okay, exceptionally stable because it doesn't want that extra electron, so it ditches it so fast that it becomes sodium ion. Sodium metal, not so stable because sodium ion is. So sodium metal will ditch an electron very quickly to become sodium ion. That's what we're taking advantage of in this reaction. Sodium metal is going to offload that electron very, very, very quickly. Okay? Because hopefully you've had an opportunity to read, or not read, watch the radical video. The radical video is talking about single electrons. What is sodium ion ditching? A single electron, which means that last reaction is probably going to run through a radical mechanism. And indeed it does. Okay? So those last two, I would argue, should really be memorized. If you see hydrogen with a metal, just add hydrogen on the same side of a double bond and just be done with it. If you see hydrogen with Lindlar's catalyst, okay, or you see this weird sodium ammonia thing, those should be memorized because those don't follow the same patterns. We need that extra information to make sure that you get those right. Okay? So what is that extra information? Okay? Lindlar's catalyst and the sodium with ammonia actually don't react with alkenes. They react only with alkynes. Okay? So when we looked at these reagents, we said, well, I said both polar and nonpolar alike. Okay? Both of these top two reagents just attack pi bonds, period. Okay? We're in the electrophilic addition section-ish, so we might just kind of classify everything together. These last two reagents will only attack nonpolar pi bonds, and they will only attack triple bonds. It has to be an alkyne. They don't react with the alkene. Right? So that's a big thing to tie to those last two reagents. They're alkyne reducing agents exclusively. Okay? The next part would be, well, how do they function? Well, H2, tiny leaving group, means not a good leaving group. So how does the hydrogen get added to the pi bond?
Probably pulled apart and stuck on there.
Stuck on opposite sides?
No, the same side.
Same side because
Syn addition.
syn addition is the exact same thing as saying they're on the same side.
It can't get away. It's so small, so unstable.
The leaving group is unstable.
Yeah.
So it fits the classification that the hydrogens have to be added on the same side. Okay, we just attacked the question from two different angles. Okay, that molecule fits in the category of the cyclic four-membered ring. The hydrogens must be added same side, which means when I look at the product of that reduction, the product of that reduction will have to be the cis alkene, because the hydrogens get added to that same side. Right? Why might that be a problem? Or why might you think that that is a bad thing?
Because if you're looking for a trans product, you can't get it with.
So we could go, well, I wanted the trans product. What else could we go with? When we look at alkene formation, which pi bond do we want? We typically want the trans because it's the most stable. This one won't do that. Right? So it is a common way to test it because everybody goes, oh, I want the most stable pi bond. No, we want the most stable pi bond that results from the mechanism that allows it to happen. Okay? In this case, because hydrogen is such a bad leaving group, it can only add on the same side. The most stable pi bond ends up being the least stable pi bond because it's the only one that can form. Kind of like our E2 elimination. Because when we say E2, we should be thinking kind of like that direction. It's not cation. What are you doing with that? Anticoplanar. Okay? It's a backside attack mechanism. We have to have that anticoplanar alignment. Okay? That's what dictates the product in the elimination. That may not be the most stable product, but that alignment has to happen. The same thing is happening here. To run the addition, we have to have the hydrogens added to the same side, which means we end up with the cis pi bond, the less stable one. Okay? So it's still holding some of the characteristics of our other reactions. Hydrogen's getting added on the same side because it's a bad leaving group. Okay? If we look at the next one, the sodium with the ammonia. That one's got to be doing something really freaking weird. Okay, we've got sodium as a solid. That's odd. It can only give up one electron, so it's a radical. That's odd. The only source of hydrogen is a positive hydrogen, at best, from our ammonia. Okay, and I need to put two hydrogens on. Okay, everything about this bottom one is screaming, what the hell is possibly going on? Okay. So let's, do I want to poke a little closer? Yeah, let's poke a little closer. Well, not quite yet. Okay, let's see. Yeah, just making sure. So this is just our summary slide of the reduction. It cleans it up so that we can see all those pieces. Okay? The alkyne, if we use H2 and platinum or palladium, would go to the alkene. Alkenes react, and it reduces all the way down. Okay, kind of makes sense? Okay. I do want to address one thing. Where is it? Lindner's catalyst. Okay, because it's not on the next slide. Lindner's catalyst is still a metal catalyst. It still brings in platinum or palladium. Why is that potentially problematic?
Heavy metal contamination? Or it still does that other reaction?
Platinum and palladium showed up with the alkenes. Shouldn't it reduce it? Yes. Okay, what makes Lindlar's catalyst so special is it's not just platinum and palladium. We're adding something else. What is that something else doing?
Changing the reactivity.
It's changing the reactivity, preventing the alkene from reacting. What is that something else? Okay. It's usually some kind of carbonate. Okay. So really, if you see platinum and palladium with something else, okay, that's putting you into the Lindlar's catalyst category, and you should be stopping at the alkene. Okay. And why something else? Well, I've seen carbonates. I've seen sulfates. Okay. Well, carbonate's a -2, sulfate's a -2. Okay. Which means I would need some metal ion. I've seen barium carbonates and barium sulfates. Okay. I've seen, all I remember is barium. Oh, I have seen calcium. I've seen calcium carbonates in these. Okay. So pretty much anything with platinum and palladium, it's Lindlar's catalyst, stop at the alkene. Okay. If you just see platinum and palladium, that's super reactive, go all the way down. Fully reduce it. Okay? That's the extra piece that we need to know with Lindlar's catalyst. Okay? So you can see it as Lindlar's catalyst, you can see it as platinum or palladium with barium carbonate, with calcium carbonate, with barium sulfate, with calcium sulfate. Okay? It can show up with a bunch of other pieces. And there's actually another thing that we could add in here. Okay? I have also seen it written out as hopefully I spelled that right. Okay, good. You're at least saying it, so you're saying it the way I thought it was supposed to be spelled, so that's good. Poisoned platinum. Is that barium carbonate?
No.
Is that barium sulfate?
It's something else.
It's something else, which means it's Lindlar's catalyst. Okay? So literally, if you see platinum and hydrogen, reduce it. If you see platinum with something else, I don't care what that something else is, it's Lindlar's. Okay? Or it is the Lindlar's category is really what we should be saying. Okay? So poisoned is just saying it stops. We've inhibited its ability to continue to react. That's what that poison is saying. Yes?
What is Lindlar's catalyst?
It's platinum or palladium with something else.
Okay.
Okay? I think
Super complicated.
officially, I'm going to go way out on a limb and just kind of guess. I think it's barium carbonate. I think is officially Lindlar's. Okay? But really what that category gets referenced as is the category of reagents that stops the reduction.
Okay.
Right? That's Lindlar's catalyst. Okay? The specifics of what that something is, not really relevant.
Super complex questions. I'll look it up on my own.
I wouldn't say it's super complex. It's just I've never bothered to memorize reagents. So, right? Kind of makes sense? Okay, so what happens with the next one? So what is going on within this one? What is the most reactive thing there?
The sodium metal.
The sodium metal. It is reactive because why?
It has a single electron.
It has a single electron. Does it want that single electron? No, so it's going to offload it. When we talk about radical mechanisms, we're moving single electrons to the space where a bond will form. Okay, so it's different than the standard mechanisms we've looked at. Because in the standard mechanisms, we're moving 2 electrons. I move the electrons to the atom that I want to be making the bond with. Okay? Or I'm moving the electrons from a bond to the atom that I'm trying to break the bond with. Radicals don't do that because we can only move 1 electron. So we're moving it to the space where the bond should form. Okay? What is the most reactive thing through the rest of that?
Hydrogen?
The hydrogen is connected to a nitrogen through what kind of bond?
Sigma bond.
A sigma bond. Is there a bond that is higher energy than a sigma bond? A pi bond. So what happens? The electrons from that sodium, that single electron, goes, I need some place to stabilize. I'm going to try and give it to the pi bond. What's the problem with giving it to the pi bond? There's already too many electrons, or enough electrons there. So what happens is the pi bond breaks. We show the electrons going into the space between. Okay? Isn't there a song about that? Sorry.
One Direction.
Is it really? That's kind of hilarious. So the space between. I'm now making a bond between that far right carbon and the sodium. What happened to the other electron in that bond?
Probably reacted with the other sodium, or it's just chilling.
If it reacts with another sodium, I'm saying sodium, alkyne, sodium. And I would have what kind of a mechanism?
Set addition. Or an addition.
I would have a termolecular mechanism because I have 2 sodium atoms and an alkyne. That's 3 different molecules all reacting at the same time. How successful are threesomes?
No.
No.
Not. Okay, so bad idea. Don't bring sodium in.
So then there's a radical on carbon.
What happened to the other electron? The other electron has to go to the only place it can go. It can't follow the original carbon. It can't go to the sodium because the whole point of the sodium was to get rid of electrons. So what happens? I show that that single electron in that atom goes to that carbon. Okay? Now we encounter a potential issue here. Okay? And in fact, let's not actually address that issue yet. What kind of bond, or where's the most reactive thing now in that molecule? Does everybody agree? The radical? Because the difference between sodium and carbon isn't like sodium as a positive and carbon's a negative, and a negatively charged species isn't as reactive as a radical. Charge is kind of a big deal. Okay? That radical is actually not charged. If we attempt to determine the charge on that carbon, it's neutral. The charged carbon is by far more reactive. So the next step is going to be to do what?
Neutralize the charge.
I need to neutralize that negative charge. Does carbon want to be negative? No. Which means that carbon is exceptionally reactive as what? Okay. And since I already heard it, nucleophile. Fantastic. Where's there a positive atom other than hydrogen in that structure? Sodium is an ionic bond, and that ionic bond by definition breaks because we know sodium ion is a spectator. So yes, sodium as a positive atom doesn't do anything useful. The nitrogen? The nitrogen in the ammonia is positive? That nitrogen, that lowly little nitrogen there is partially positive?
No, it's partially negative.
It's partially negative. I like where you're going with that idea, but it doesn't fit the pattern of our carbon acting as a nucleophile. Wait, what? The hydrogens are partially positive? Why is that? Because nitrogen is more electronegative, which would mean that species would act as
A leading group. Well, actually, you got the hydrogen and electrified.
we could say an electrophile, and I'm going to say no, that does not fit our category for an electrophile. What is an electrophile? Accepting electrons, the atom that accepts electrons, can be what? Anything other than hydrogen.
Acid.
And what is the atom accepting electrons in this case?
Hydrogen.
Hydrogen. So can the hydrogen be an electrophile? No, that does not fit our definition because there's a better definition. What is that better definition? An acid. What is our negative charge acting as?
A base.
A base. This is an acid-base step. Okay? This acid-base step, I don't know why I'm stair-stepping this all the way down. I'm mildly irritated at myself. Puts the hydrogen on there. We would then end up with a negative nitrogen. Okay? Okay? And there was this, leaving group. A little weird to call it a leaving group because it's an acid-base step, but let's just run with it. Is nitrogen a good leaving group?
Yeah.
Okay? Is hydroxide a good leaving group? No. Is nitrogen a better leaving group than hydroxide?
No.
Okay, so there's a fun question. Let's address that. Which is the better leaving group, hydroxide or the amide? Okay, hydroxide, and that is because it's more electronegative, so what does it do? It stabilizes the electrons better. Okay? So hydroxide's a bad leaving group, according to your definition, but it's a better leaving group than the amide. So should the amide act as a leaving group?
No.
Uh-oh. What does that suggest about our mechanism? That it sucks. Hydroxide is not a bad leaving group all of the time. Hydroxide is typically a bad leaving group because what is it leaving into? An acidic condition, like water. Hydroxide is not stable in water because it's a strong base and it would react. Okay? That would be the leveling effect. Did you just stab each other?
No.
Okay. You saw one person smiling and the other person wincing in pain. Okay? It's the leveling effect that was sort of addressed back in chapter 7. Okay? So why would this be a good thing to happen then? So that's a horrible leaving group. What are we comparing that negative nitrogen to?
Negative carbon.
A negative carbon. Which one's more stable? A negative nitrogen because it's more electronegative. So can I stabilize, or is that negative nitrogen actually a good thing here? Yes. That is actually a valid thing to have happen.
Can't
Okay?
it interact with the new sodium ions?
And it can interact with the new sodium ion, and people like to show, the electrons go to the sodium to form what bond? An ionic bond. And what do ionic bonds do? They break. So don't do that. Just don't. Okay? We'll talk about in second semester some cases where we can start to consider why that might stabilize and have an effect, but we need to have a comparative system that allows us to do that. Okay? At no point have we addressed this semester why that would ever happen. Okay? So don't do that. Don't start showing electrons making ionic bonds. It's a bad idea. Okay? What happened to the other half of our structure? Said another way, is this black structure the result of just the arrow shown? No, what's wrong with it? I'm missing literally the other half of the structure. Should we draw that?
Probably.
Yeah, that's a good idea. I think we should draw that. Is that a stable structure? No, why not? Radical. We don't like radicals, so what happens?
Does it do the same thing with another sodium? Except no, I don't like that one.
Okay. But now we bring in an issue. Because when we go through to draw this out, we now have a lone pair of electrons. That lone pair of electrons is taking up space. Okay? Which means the geometry of that position is what? I know that's hard, so don't think about it there, think about it down here. Okay? If we added a lone pair, it would be trigonal planar, which means at this stage, we now have the option of showing cis or trans. where does the R group go? Should I draw the R group down here? Or should I draw the R group up here? Why should I draw the R group up?
Because we know what the data says.
Because it says it's trans. Okay. Fair answer. What did you get?
Because we know what it ends up as.
Okay, so same answer. Because we know it ends up at trans. Why would we favor the trans alignment at this stage?
To avoid like the steric.
Okay. To avoid the steric repulsion of those R groups. Those R groups are naturally going to levitate, not levitate, but you get the idea, away from each other into the trans alignment. There's no stereochemistry or regiochemistry of the reaction forcing one or the other. Okay? We just now have the opportunity for the R groups to say, have this, I don't want to be near you. I can go away. Okay? Generating the lone pair now, come on, at that lower position, there's our negative charge. Is that stable?
No.
So what does it do? It removes the hydrogen from a second ammonia, and we end up with our final product. Okay? This is what is known as a radical anion reaction. Why?
Because you used a radical.
We used a radical, and we made an anion. It's a radical anion mechanism. Okay? Kind of makes sense? Okay. Ultimately, what are you responsible for? You're responsible for the end product. The mechanism behind this, I want you to see so you can understand why it's there. Whether you decide to memorize it is up to you. Okay? You could theoretically see a question. Can I clear everything? Can I clear everything?
Yeah.
You could theoretically see a question that is, which of the following species is formed in this mechanism? Okay? In which case do you need to know the mechanism? If I ask which of the following species forms in the reaction above as an intermediate? Do you need to know the mechanism? You would have to know why each of those structures don't work. You would have to understand the mechanism behind it. Okay? If you don't know the mechanism, you should be able to use your skills that we've talked about through this class to be like, how would this reaction work to allow or disallow one of those as valid intermediates? Okay? So if you encounter a question that is, which of the following is an intermediate for this reaction? If you don't know the mechanism, what you might do is just delay answering that question until you have the time to start to draw out what that mechanism is. Or maybe you've memorized it. Like for this one, if you memorize that it was a radical anion mechanism, which of those is a radical and an anion? There's only one. There's my answer. Okay? So you can memorize some information. It's just a question of how you want to balance that out. There's a lot of stuff that you have to process through. Memorizing it all will be impossible for the vast majority of people. Okay? Make sense? Yes.
Do you have to use only sodium, or can you use other group 1 metals?
You can use other group 1 metals.
Okay. So this is not relying completely on sodium. Like you said.
True. You could use pretty much any one. One of the issues about using other metals, though, is what?
They're even more reactive.
They are more reactive. The more reactive they become, the more likely you could be running side reactions to do other things that you didn't want to have happen. Okay? So sodium tends to be the most common one. I think I've seen potassium. I've never seen rubidium or cesium. Okay? One of the reasons why we might just not worry about that is, remember, Unit 1, probably day 1, what did we do to our periodic table? We cut off most of the periodic table. We don't care about a large percentage of it. Okay? So we don't have to dig into those. Because we know chemistry, groups and families all react similarly, they would probably do something similar, but they might also do a bunch of other crazy stuff. Okay. So if you wanted a prettier version of the mechanism, right, you can look at the slides. If it all looks like empty white space, it doesn't. It looks like it shows up, so that's okay. We won't worry about that. Okay? This reagent also shows up in this circumstance. Okay? We take sodium metal and we take ammonia and we react it with benzene. Do benzenes react?
Not typically.
Not typically. Why would they react now? Because sodium is so awesomely reactive. Okay? So sodium's going to force it to react. In that case, that sequence of reagents, sodium and ammonia, does what kind of reaction? Yeah, addition. All the way up the top.
Anti-reduction.
A reduction. Okay? As a reduction, what's going to happen? You need to be adding hydrogens. So put hydrogens onto the benzene. What becomes the problem with that? There's a bunch of places that you could place the hydrogen. Okay? That reaction runs almost identical to the one up here. Okay? It's a little bit trickier to deal with because if we only add hydrogens to one pi bond, the other two pi bonds are in conjugation with each other. Because they're in conjugation, they're going to be like, well, if I just ditch those hydrogens, I become that super cool benzene again. Okay? I have to remove that teamwork. So how do I do it? I react one of the pi bonds, do resonance. I've now broken the conjugation. Now I can complete the reduction. So the final product becomes more stable. Okay? This is looking at aromatic rings as reaction or reagents. Aromatic rings are officially in second semester. We will talk about it again in second semester, but you can do some pretty cool stuff with it that I thought was up there that apparently is not. Okay? So you don't need to stress about that. I just want you to be aware there's a little preview for second semester. Okay? Next kind of big part, oxygen in substitution and elimination. Okay? We've already kind of looked at these. Oxygen, synthetically useful because of lone pairs. What do the lone pairs do?
Provide electrons.
Provide electrons, which would mean? Thank you. I know it was nice and vague. It could act as a nucleophile, or it could act as a base. Oxygen is also a special reagent to have on our structure because it is highly electronegative, which does what?
Makes it an electrophile.
Okay. It can make the carbon, where the oxygen is connected, electrophilic. And by that exact same token, what can it do? It can remove the electrons from the hydrogen, making the hydrogen acidic. Okay? So this is really neat. That oxygen on our structure is insanely synthetically useful. Right? But that can also be a bad thing. I now get access to the entire spectrum of reactions, which means when I add a reagent, I have access to the entire spectrum of reactions. Which means an alcohol could go every direction. Okay? This becomes difficult as a student because now you have to look at an alcohol and recognize that it can do every single reaction. Okay? Depending on the conditions that it's under. Okay? As a synthetic chemist, this is now also a dangerous functional group. Because when we go through to make something, is that something only going to have one functionality? No. If you look at any of the drugs out there in the world, there's a lot of different functional groups in each of those compounds. Which means to make one of them, I also have to make sure the others didn't react. If there's an alcohol in my structure, that alcohol could react at any time through the whole process. Right? So when we think about the alcohol functional group, we have to be aware of all of the chemistries that are available to it. And what we might decide is that that is a bad thing. So what might I do to limit all of those reactions? Get rid of the alcohol. Turn it into something else that isn't as reactive. Right? For instance, what if I turned it into a halide?
Halides fairly reactive.
It has lone pairs just like oxygen. Can the halogen act as a nucleophile or a base? Can this halogen on this structure act as a nucleophile and a base? No, because it's happy with one bond. So changing it to a halogen, I lose the nucleophile base characteristics. Right? It is highly electronegative, so damn it, Mike, it's still reactive. It makes that carbon electrophilic. It absolutely does. What does it do to the hydrogen?
What hydrogen?
Oh.
Because
It doesn't matter what you do, you're going to play into my hands anyway. You might as well just play along.
yeah.
Okay? The halogen functional group only has one form of reactivity. That carbon is electrophilic. Okay? So when we think about our reactions, we need to be able to look at a functional group or an atom and say, how does it affect the overall structure? What does that open me up to? Okay? As a potential good thing and as a potential bad thing. Okay? So when we go through and look at this, an alcohol functional group can get converted out to halogens fairly quickly. Is the OH a good leaving group? So what do you need to do? Make it a good leaving group. One option, protonate it. Because if I protonate it, what happens? Okay? It would be a phenomenal leaving group as water. If I want to replace it with a halogen, what else do I need to add? A halide, right? So that it can nucleophilically attack that carbocation or do a backside attack. So, hydrochloric acid, hydroiodic acid, hydrobromic acid. All of them are doing the same thing. Make the leaving group better. Now let me do my substitution reaction. Okay? You'll notice with HCl, it's not just HCl. Why did we add something else that I didn't add to HI or HBr? Well, damn, that's kind of weird. Well, what's the difference between HI, HBr, and HCl? Size. What would size do? Shh.
No, go ahead.
Somebody else. What would size do?
Change its stability.
Yes, change the stability of what?
The negative charge.
The negative charge. How does it change the stability? What is the difference between I versus Cl? I is bigger. If I is bigger, what does that mean about HI versus HCl?
It's easier for the hydrogen to leave.
It's easier for the hydrogen not to leave, but to come off or to be removed, which means HI is more acidic. If it is more acidic, can it protonate the oxygen faster? Yep. Which then means leaving group is better, leaves faster. Okay? HCl isn't quite as strong of an acid. It turns out that it's not quite strong enough to force that reaction to happen at a useful rate. So what do? We add a catalyst. The catalyst makes the oxygen a better leaving group so that the chloride can attack and kick it off and it runs faster. Okay? I don't need that extra consideration for the HI and the HBr because they're already strong enough acids. Right? And for those of you wondering, isn't HCl a strong acid? Yes, that doesn't mean it's strong enough. Okay? There's plenty of people strong in this classroom. That doesn't mean they're strong enough to become the world's strongest person. Okay? So in this case, we need that extra catalyst. If we move to the other side, what's now changed? Are we still adding an acid? Yes, we're adding sulfuric acid. Is that a strong acid?
Yes.
Yes. What is the difference between sulfuric acid and HCl, HI, HBr? What does that resonance do to the sulfate?
It neutralizes its nucleophilicity.
It kills its nucleophilicity, which means when we look at the right-hand side, the conjugate base are sulfates. Those species are now not nucleophilic. Well, if they're not nucleophilic, can they do a nucleophilic attack? No. So what do we have to look for? Some other way to stabilize that forming positive charge. Where do I get electrons in the top case? We'll call it orange. Where did I get electrons to do that top reaction?
Is it from another sulfate or whatever that thing is?
A second molecule. A second molecule attacks. Why does this have to be under dilute conditions? What happens if the sulfuric acid is concentrated? All of those oxygens get protonated. If every single oxygen is protonated, do we have a nucleophile? No, because it would be positively charged. So we have to run under dilute conditions. Just enough to protonate so we have a good leaving group, so that the remaining alcohol can act as a nucleophile to attack. Why would we do that? We've converted our alcohol into an ether. Does the alcohol have lots of chemistry?
Yes.
Yes. Does an ether have lots of chemistry? It's a harder question. What is the identity of this compound? Diethyl ether. What can you tell me about diethyl ether?
Weak dipole.
Weak dipoles, yep. Not soluble in water. When did we use diethyl ether? For solubility. Okay, to dissolve almost all of our reactions. Because what was the role of diethyl ether? Should be able to attach a name to it. Begins with an S. It's the solvent. Why would we choose diethyl ether as a solvent? It doesn't react. What happens to the reactivity of an ether? Falls through the floor. We get virtually no reactivity with an ether. Why would I do that? Because maybe I don't want the freaking alcohol to react. I'm now killing it by turning it into an ether. It's no longer active. Right? I can still hold some of the polarity from that oxygen, but I've now reduced its reactivity ability, which means if there's another functional group somewhere else in the structure, I don't have to worry about the alcohol potentially being an issue and messing with that chemistry. I've now neutralized it. What happens in the lower right? We now up to concentrated. Do I have any nucleophile now? No, now there's no nucleophiles because under concentrated conditions, every single oxygen gets protonated, which means they're all positively charged, which means there is no nucleophile. Where do I get electrons to stabilize a forming carbocation?
Within the structure.
Okay, a carbocation that I might say is located at the alpha position.
The beta carbon.
The beta carbon, what's at that beta position?
Hydrogen.
Hydrogen. I could run a beta elimination. What was the tip-off that I was doing an elimination reaction? I formed a pi bond. Okay? By identifying that reaction type, you knew you did an elimination. What happens when we do an elimination? We lose a hydrogen. Okay? So the key words of being able to find what these things are and bring meaning to them becomes important. Okay? We don't think in just symbols, we also think with words. Use those words to help piece your way through a reaction. There are other activations. We'll talk about these in second semester. Okay? We can run with thionyl chloride in a couple different conditions. We can run with TSCl. TSCl is just a fancy term for tosyl chloride. And PX3, phosphorus with chlorines or bromines. All of these ultimately change the reactivity of the alcohol. They convert them into a different functional group, which allows me to do different chemistries. What becomes more interesting about these than on the previous slide? Stereochemistry becomes vastly more important for these. So if we're thinking synthetically, what's going to be the better reactions? This slide or the previous? This slide. Okay? If we're thinking for a test question, we might ask a reaction about these. Okay? But we'll probably ask a reaction about these too, because these are simpler to deal with because they don't have as much stereochemical issues to worry about. Why is it not as much? So this isn't a stereocenter. Oh, it absolutely is. Why do I not need to worry about stereochemistry then? What mechanism must this be going under? SN2 would mean I get one stereocenter. In this case, if I'm not mentioning it, it's because it's following SN1 conditions. Okay? We're forming carbocations in almost all of these situations. Okay? In these other activations, we don't get any carbocations. Those are all simultaneous reactions. The mechanisms behind them are a little bit more complicated, still within your realm of ability, but we'll worry about them later. Ether synthesis, we really already talked about this. The main reason why I want to address it, okay, is that you'll hear this Williamson. There's two ways to make an ether. You make a good leaving group, okay, or you make a really good nucleophile. Those are your two options. Okay? Now, making a good leaving group is ultimately saying, I'm trying to make a good electrophile. Okay? The other method is make it a good nucleophile, so make it as strongly negative as possible. Williamson happened to be a guy that came up with that second method, and for whatever reason, we've decided to attach his name to it. Why? It's freaking acid-base chemistry. Like, really? Why do you get to attach your name to an acid-base reaction? Okay? I think that's pretty stupid, okay, personally. Okay. Which does mean I should probably look up what he did and when he did it, because maybe he did it really good. Maybe it is actually really interesting. Okay. But the process, we take a strong base. The strong base will deprotonate the alcohol. Why is that good? The end result of step one makes what? Strong base, this must be an acid. What happens when you remove the hydrogen? What have you just made? I made a negative oxygen, which would be the conjugate base for the record. I have a species with a lot of electrons. What kind of things have lots of electrons? Nucleophiles. I'm making a good nucleophile. That's the point of the reaction. Once I have a good nucleophile, what do I need to react it with? An electrophile. Ta-da! And I can throw in the halide functional group because the halide chemistry is only an electrophile. Okay? And I can get now a backside attack through an SN2 mechanism to make that ether. Okay? The Williamson ether synthesis allows you to make asymmetric ethers. Okay? So it's kind of cool for that. So asymmetric, we don't have the same number of carbons on each piece. Why? The parts that bring in the carbons are two entirely different structures. Right? That's why I can get asymmetric ethers. Part one, just making a good leaving group, all I have to do is add an acid. Well, then where's my carbon source? Well, it's the starting material. I get one carbon source. I get symmetric ethers. So Williamson is nicer because you can get asymmetric structures. You have two different carbon sources that allows for the synthesis cleaner of different sized carbon ethers. right? This is an important question. I'm going to leave it for you outside of class. If you're using the ACS study guide, there are multiple questions in the ACS study guide that ask the same thing. Right? How do I make an ether, or how does that ether react? You need to consider all of the steps along the way. That first step is an acid-base step. The second step is an SN2 mechanism. What's the problem with SN2 mechanisms? When I say SN2, you say? Backside attack. What's the problem with a backside attack? Steric hindrance. Attack. Okay? So I have to worry about steric hindrance. So when I go through to make these structures or these ethers, I have to be cognizant of steric hindrance in that second step. And the path I choose, if it's going to work, better minimize the steric hindrance as much as possible. Okay? So, next part, last one, are epoxides. Once we've made epoxides, we can then react them. There's two conditions under which you can react an epoxide, either basic or acidic. Okay? And really it's basic / neutral or acidic. If we run under basic conditions, that means we're going to be using a strong nucleophile. How do I know I would have a strong nucleophile under basic conditions? Okay. Why would basic conditions facilitate me having a negatively charged species floating around? Name a base. Good. I was waiting for first. That's all that was cycling through my head. Don't say first. Don't say first. Come on. First base?
Who's on first?
Never mind. NaOH. What makes NaOH reactive? The negative charge on the OH. If I'm running under basic conditions, why might I expect a strong nucleophile? I don't know. What's the charge on a nucleophile? What's the charge on a base? If I'm under basic conditions, why might I expect the presence of a strong nucleophile? Basic conditions are negative. Right? Nucleophiles are negative. If I'm going to run under basic conditions, I'm probably going to see a strong nucleophile. Why would I not see a weak nucleophile? Weak nucleophiles mean I'd have to hide that negative somehow. What would I hide it behind? I'm going to pretend I heard proton. I'm not sure you actually said that. Why would that be a problem in basic conditions? That would do an acid-base reaction. I can't do a weak nucleophile because I'd get an acid-base reaction. Right? So under basic conditions, we will have strong nucleophiles. What is that strong nucleophile going to seek out? What charge is a nucleophile? What is that nucleophile going to seek out? Positive. Where's the positive in the epoxide? And admittedly, there was a trick question. Where is the positive in the epoxide? Now you're like, oh, it was a trick question. I'm not going to answer that. Oxygen, being a more electronegative atom, does what to the electrons in the bond? It pulls them towards itself, which means the carbons become positive. Where is the positive? There's two positives. There's not one, there's two. Okay? Where's the nucleophile going to attack? I now have two choices. Okay? Why do you want to attack the red carbon? Okay? Why do I care about steric hindrance? A strong nucleophile would suggest which mechanism? SN2. And an SN2, because it is backside attack, wants the least steric hindrance. That should have been red. Bond breaks. What's the result? Our nucleophile now attacks there. Here's our R group. There's our hydrogen. Notice, what is the alignment between the oxygen and the nucleophile? They're trans. Why? Why can't the nucleophile attack from the top? Why is this a bad idea? Better.
So the steric
The oxygen has electrons. What is the nucleophile bringing in? Electrons. Why does it make no sense for the nucleophile to attack the top? There's electrons there. It's going to repel away. It can't get in there. It can only come in from the backside. What charge would my oxygen be at the end of that step?
negative.
It would be negative. Is that a good thing to end at? No. So what do I need to do? Maybe you're thinking too far out. I would need to neutralize it. How do I neutralize a negative species? Why would I protonate it? What does a negative species act as? A nucleophile or a base, which is why your suggestion of maybe I should protonate it is awesome, because what is protonation doing? An acid-base step. That oxygen is a base. I should put a proton on it, because how do I neutralize bases? I give them acids. There it is. Right? Nucleophile, OH, R group, there. Right? One of the things to watch out for is, did I have to draw it this way? Is this a sigma bond?
Yes.
Could I rotate it? Yes. Would that potentially make it look different? Yes. Would that mean you'd go, oh, that's the wrong answer because they attacked on the same side? You might. Watch out for that. Okay? We want to make sure that the nucleophile and the OH added anti to each other. If there's stereochemistry at both positions, that stereochemistry is locked in from step one. You have to make sure that even if you do a rotation, that stereochemistry is still maintained. Kind of makes sense? Okay.
You just don't have stereochemistry at the nucleophilic position.
This position doesn't have that stereochemistry, largely because what I'm trying to address is the difference in substitution, so we know where it attacks. Okay? Is there anything else that could potentially pop up that's complicated behind this? Of course there is. What conditions do we say we were running under? Basics. What did we say we added here? Acid. How do you add an acid to a basic environment? You're like, damn it, I can't do that. You can. It's really neat. It's called step 1, go under basic conditions. Step 2, make it acidic. Okay? Step 1 and step 2. They have to be separate steps. Okay? This does not mean one's above the arrow and the other one's below the arrow. It has to say 1, 2. Okay? Which is a common issue. We could get students going through and saying, well, I'm going to do hydroxide and H+. That ain't going to work. But if I go through and say 1, 2, now it does. Okay? So you have to be very careful to acknowledge the meaning behind those 1 and 2. Those 1 and 2 are separate reactions, not mechanisms. Okay? So it's saying I mix these things, I let it do its thing for a little while, then I stopped it, I did some stuff to it, I took that stuff and I added some more reagent to it. Okay? Step 2. That's the meaning of each of those numbers. Okay? And there we step through it. So what happens here? We're under acidic conditions. What's the most reactive thing? The acid, I completely agree, because it's acidic conditions. That's why we have H plus floating around. So what do I need to do to that H plus? I need to neutralize it. What would I need to neutralize it? We need a base. Also, I would need electrons. Where could I get those electrons from? I could get them from the oxygen. Does the oxygen want to be positive? No, so that bond is dying to bust open. Our nucleophile. Should that nucleophile be a strong nucleophile? What charge would a strong nucleophile be? Negative. What conditions am I under? Acidic. What charge should never appear in acidic environments? A negative, which means that nucleophile is by definition going to be weak. There are again two positions the nucleophile could attack. Blue versus purple. Where does the nucleophile attack? Why are you now saying blue?
More substitute.
Why do I care about substitution? We don't form a carbocation, so that doesn't quite fly with me. It's a weak nucleophile. Where would weak nucleophiles fit? Good. Way to follow off of that, because that was really vague. That's awesome. SN1. SN1's favor attacks where? The more substituted position because of carbocations. There's no carbocation forming here, though. Okay? Because we know that is a weak nucleophile, it's going to attack there. That's going to cause the ring to break open. The result, oxygen. Okay? Because it was a weak nucleophile, it likely started neutral, which means its charge now would probably be positive. So we'd have to follow this up with another step where we removed, in all likelihood, a hydrogen. Okay? Why does this become tricky for students? So let's jump to the summary now. Under basic conditions, where does your nucleophile attack? Where does it end? The least substitute. Under acidic conditions, where does the nucleophile attack? The more substitute. And this was, oh my God, there's no freaking exceptions. Okay? This isn't an exception. This is following the basic chemistry, and I apologize for basic. Okay? This is following the chemistry to predict where those things are going to happen. Okay? That's what you should be tracking. If you don't want to do that, or already like my brain is already turned into a more sponge than it can possibly be, I can't process anymore, then you're going to have to memorize it. Okay? Or just guess. Where do we get our epoxides from? MCPBA or some other peroxy acid. Okay? That's the easiest place to get them from. Okay? And with that, we now magically become radicals, which was all online. Oh, see, there's the birch. That's the slide I thought was going to pop up. If you wanted that mechanism for the birch, there it is. Neato. Conjugated pi systems do all sorts of weird things. Okay, the conjugated pi systems we already saw, okay, with HBr. Okay, we end up with two potential products, kinetic and thermodynamic. Okay, we can do conjugated pi systems under radical conditions. Or sorry, this one isn't conjugated. We can do radicals, okay, by themselves, and they'll polymerize outwards. Okay, so we can get radical polymerizations. What if we did something like this? Radical conditions, so I'm going to get that polymerization, but now there's two potential sources of pi bonds that could react. What happens with products? This becomes exciting. I'm not going to bother to draw it. It explodes. You get reactions happening virtually every which direction. Right? You're going to get chains that connect to chains. This is known as cross polymerization. Okay? What happens if we just delete that initiator? Well, now there's no radicals, so there couldn't possibly be a reaction. Except we do have positives and negatives due to resonance within those pi systems. Those positives and negatives, if they align properly, will allow for a fancy reaction. That fancy reaction won a Nobel Prize, known as the Diels-Alder reaction. Okay? If we change that alignment, we now form a cyclic hexene. That cyclic structure is more stable than the starting materials, and that's what facilitates that product happening. Okay? Stereochemistry there, not fun to deal with. It's neat. It's fun. Well, I think it's fun, but it's not fun to be tested on. Okay? Because it is very spatially challenging. Okay? Officially, we'll talk about that in second semester. And so with the last 1 minute, what are your questions?
Woo!
The answers.
You're like, dude, I don't have any questions. I just wanted you to stop talking.
What's your best